Hello everyone, welcome to the lecture Coordinate Systems in the International Master's Program Geodetic Engineering. My name is Jan-Henrik Haunert. You will see me regularly in the lecture Geoinformation Systems during the International Master's Program in the first semester. However, today I'm presenting in the lecture Coordinate Systems some basics about map projections. And before I come to that, I would like to give a brief overview about the different types of coordinate systems that are used in geographic information systems and in geodesy in particular. So, first of all, what you know already is that we often have coordinates in this Earth-centered Cartesian coordinate system, where we have x, y, and z coordinates. Well, this is Earth-centered, so the origin of the coordinate system is in the center of the Earth. Then we have the x-axis pointing towards Greenwich meridian in the equator plane, and also in the plane of the equator we have the y-axis perpendicular to the x-axis. And then the z-axis is pointing towards the North Pole, perpendicular to both the x and y-axis. Well, these coordinates are often used, for example, to give the position of a GPS satellite somewhere in space. Of course, there you need this three-dimensional coordinate system. This is, however, very inconvenient to deal with points on the surface of Earth. If I tell you that I am at coordinates 20,000 kilometers x and 15,000 kilometers y and 12,000 kilometers z, then it doesn't tell you much about your position on Earth. It's not very nice, not very convenient to handle. And therefore, for everything that is on the Earth's surface, it is much more convenient to refer to it in terms of latitude, longitude, latitude phi, longitude lambda. So that can be the spherical coordinates, so meaning these angles are defined on a sphere, or it can refer to the ellipsoid, so then we are talking of ellipsoidal coordinates, phi and lambda. These are angles, of course. And then last but not least, we have these projected coordinates, right? Something like easting x and northing y. That could be a map coordinate system. To convert these coordinates from one coordinate system to another, well, there's this very simple mathematical equation here defining the relationship between the Earth-centered Cartesian coordinates and the spherical coordinates phi lambda. Yeah? But for this one here, that is actually not that easy to define. There it's not just a single equation that defines this relationship, because that relationship, it depends on which map projection you choose. And that is exactly the topic of today's lecture, namely, well, different map projections and their properties. How to design map projections and how to analyze them. And how to apply them, of course, as well. Well, so that's our task for today, to talk about the relationship between these spherical coordinates phi lambda and the plane coordinates, the projected coordinates x, y. Well, that's done with a map projection, of course, mapping the sphere to a plane, and that is usually, or it is always, it implies some distortions. So if you think maybe of an orange fruit where you need to peel, so you take the peel out of the orange and try to flatten it into the plane, that is impossible without distortions. So somehow we need to deal with distortions here. We need to tolerate and deal with distortions. And then there's not just one map projection for all purposes. We need different map projections because, well, in some cases maybe we would rather tolerate distortions of areas. In other cases we would rather tolerate distortions of angles. That depends heavily on the application. Also, sometimes we would like to display the entire Earth in a map, and sometimes we have a very small area on the surface of the Earth, and also then we would probably not use the same map projection for these two different applications. So therefore, well, if I go back to this slide here, there's not just one answer on how to solve this problem, the to-do here on this slide, but it depends on the application which map projection to choose. Okay, so that brings me to the outline of the lecture today. What I would like to present in this one lecture about map projections is, well, I will first of all talk about the most basic map projection that exists, or let's say the most basic cylindrical map projection, which is the Plate-Carré projection. And after that, I would like to talk more generally about cylindrical projections. So what is a cylindrical projection? Which properties does it have? Next, I'm talking about the Mercator projection, which is probably the most important cylindrical projection that exists, or maybe even the most important projection of all. And finally, I will also talk about the cylindrical equal area projection. So that is a special kind of cylindrical projection where areas are preserved and not distorted. Whereas in these cylindrical equal area projections, as we will see, the angles are quite severely distorted. So, first of all, the Plate-Carré projection. That is really rather simple. What we look at first is the surface of the Earth. Let's assume it's a sphere that is sufficient for today. We are not going to deal with ellipsoidal coordinates here. So let's assume we have a sphere, and on this sphere we have this grid of lines of equal latitude and lines of equal longitude. I think in this visualization here that should be something like 10 degrees spacing between these different lines. But of course you can imagine that they are arbitrarily dense, these lines, because not just 10 degrees define this grid. You could also choose a finer grid, of course. And what I'm doing here is kind of the easy way. I'm constructing the map projection now to show you also how this is defined and how you could get to the projected map after all. Well, what you can do first of all is look at one of these columns, I would say, between these two adjacent meridians, and then you have these surface elements here displayed in green and red. And what we do then with this Plate-Carré projection is that simply each of these surface elements is displayed as a square in the map. So basically, well, that is fine with these vertical lines here, because they, on the Earth's surface, actually they all have the same length. So you see this this green and the red line, and the green and this red line, and so on. They all have the same length. And similarly, we display them in the map with the same length. However, if you look at these horizontal lines here, this of course is longer than here, close to the North Pole. But still, in the map, we display them with the same horizontal length. And well, you can guess already that we have rather high distortion in terms of area, in particular, close to the pole. Okay, so that is geometrically how you can visualize this Poincaré projection. Let's get a bit more into the mathematics. Of course, we have this x axis that you can imagine here at the equator. You can imagine this y-axis here from the equator pointing towards the North Pole. And now what we can do then is that we simply say the Poincaré projection is obtained by saying easting x is equal to lambda and northing y is equal to phi. And that is what you get then. So this is now the map projected with this Poincaré projection. Here I'm assuming that this lambda and phi is measured in degrees. So accordingly you will have this coordinate system here from minus 180 degrees to plus 180 degrees. That is just in total 360 degrees. It's the whole perimeter of the Earth. And of course here we have the South Pole at minus 90 degrees latitude and the North Pole at plus 90 degrees latitude. Okay, so that is fairly easy. Usually we would like to have a map with a metric system, so where you have meter instead of degree as a unit, and that is done simply using a constant scaling factor. So of course this pi divided by 180 degrees times the Earth's radius r. And then, well, you see this map doesn't change at all, only these units here, they change. So we have now minus 20,000 kilometers here and plus 20,000 kilometers there. And in total it's 40,000 kilometers, which is roughly the perimeter of the Earth at its equator. So what we have then is, of course, here a very simple mapping function. Mapping phi lambda to xy, and that is why I was saying that this is the most basic mapping function that exists. That is this Poincaré projection. Okay, let's continue. What are the properties of this Poincaré projection? First of all, we have distortions. Well, in particular with respect to these aspect ratios of the shapes. Well, as a German, of course, I am used to see a proper map of Germany with the correct aspect ratio. And if I see this picture here, I will immediately recognize that this is not my country. Yeah, it is distorted, it is squeezed in vertical direction and kind of extended in horizontal direction. How does that happen? Well, Germany is quite far up north, yeah, and there we already have these lines of equal longitude, the meridians rather close to each other. So if we now use this surface element here, if we take this surface element and project it into this square, then we have a rather skinny vertical rectangle transformed into a square, and that causes this change of the aspect ratio, which we also see in these geographical shapes like the shape of Germany. Well, also with the same reason, or for the same reason, also the angle changes. Yeah, so we have here, for example, in red, we see this is a rather small angle, acute angle, maybe 20 degrees, and here it's 45 degrees. So that is also a consequence of applying this Poincaré projection, that the angles are heavily distorted. And also the areas change. That is, of course, also a consequence of this distortion happening here. So here we have a rather small surface element projected into a square, but further south we have maybe a larger surface element projected into a square of the same size. And that means, of course, that the relations between the sizes of areas, they are not preserved. That is meant here with area distortion. An advantage of this simple map projection is, of course, first of all, its simplicity. Simplicity is always a nice feature, but an advantage is also that the length of the equator is preserved and the length of every meridian is preserved. So if we go back to, if we go back to this slide here, you can see that the equator is presented at exactly the correct length, and the same with these meridians from minus 10,000 kilometers to plus 10,000 kilometers. That reflects actually half the perimeter of Earth from the South Pole to the North Pole. Well, here we are. That is what I wanted to show you. And with that, we have actually accomplished this task now that we have the relationship between these spherical ellipsoidal coordinates and these projected coordinates, right? So that was our equation here. I'm assuming here lambda and phi in radiant, so that is not degree, but something between 0 and 2 pi. So therefore I don't need this conversion factor pi divided by 180. It is just r times lambda. And this relationship here establishes now the relationship between the picture in the middle and the one on the right hand. But also you can, of course, now convert between these projected coordinates and these Earth-centered Cartesian coordinates. Then you would have to go first from the projected coordinates to the spherical coordinates, and from there, via this equation, to the Earth-centered Cartesian coordinates. Well, that is pretty straightforward, I would say. So far about the most basic map projection, the plat carré projection, but what I would like to present next is about the cylindrical projections. Well, what we have there in general, first of all, the plat carré projection is one example of a cylindrical projection. And that is because you can assume this cylinder wrapped around the Earth, or around the sphere. Now what we do here is basically that we project these meridians to vertical lines, that is shown here, and after that you kind of unfold and flatten the cylinder, and then you have the map. So that is one way how to explain the plat carré projection. And but it is not the only cylindrical map projection, of course, because cylindrical projections is like a whole family of map projections. So what is common for all cylindrical projections? I should say for all cylindrical projections in normal position. There are also other positions well, I will come to that later, but for all cylindrical projections in normal position, we have lines of equal latitude mapped to horizontal lines. So here you can see lines of equal latitude. It's, well, that is here, this horizontal line here, that is in the map projection is displayed like this. That is one important property of cylindrical map projections. Then meridians are mapped to vertical lines. Well, you can see that here we have these meridians or lines of equal longitude. Those are the meridians. Those are mapped to vertical lines. And finally, the equator is scaled with a constant factor, often with 1. So that means we have no distortion, length preservation at the equator. However, what is Different among the different cylindrical projections is that these distances between the lines of equal latitude, they are not necessarily uniform, as in this example with the Plat-Carré projection. There we have these uniform distances. But in general, for cylindrical projections, we can have these non-uniform distances. That can look like this, for example. And before I come to the mathematical equation for that, I would like to present you some examples, maybe. I'm moving over to the whiteboard for that. Okay, just to show you that in fact, well, there are different cylindrical projections, and you can see immediately, if you see the pattern of meridians and lines of equal latitude, you can see immediately whether that's a cylindrical projection or not. Let's take an example. Okay, let's look at this one here. Maybe I have, these are my meridians, and maybe I have now lines of equal latitude like this. So if you see a map like this, and then it's the question, is this a cylindrical map projection? You should be able to decide immediately, no, it's not a cylindrical map projection, because here we have these meridians not mapped to vertical lines. So that is not a cylindrical map projection. If you see something like this, however, meridians displayed as vertical lines, then the equator as a horizontal line, all the other lines of equal latitude are also displayed here as horizontal lines. Maybe the distance is getting smaller towards the South Pole, maybe the same towards the North Pole, so there we have smaller distances like this. So that is now a cylindrical map projection, because we have vertical lines representing meridians, horizontal lines representing lines of equal latitude, not necessarily uniform spacing between the lines of equal latitude, but uniform spacing between the lines of equal longitude, so between the meridians. There we have uniform spacing. Also this one here, let's take another example. This is our map. We have again meridians mapped as vertical lines. Well, that's as vertical I can draw, I would say. And here we have the equator, and maybe here we have, first we have small distances, and then they are getting larger towards the poles. So it's exactly the opposite of the first one here. It's that one here, where the distances between the lines of equal latitude are getting larger and larger towards the poles, but still it's still a cylindrical map projection. And of course then we had this other example where we had uniform spacing not only of these meridians, but also of the lines of equal latitude. So then it's still a cylindrical map projection. Okay, with that I'd like to continue with my slides. Well, now what we need to do is, of course, we need to think more about the mathematics behind this. This was all nice drawing and visualization, but of course we want to compute also, and therefore we need a map projection or an equation defining this mapping. And in general, what we have in cylindrical map projections is, first of all, this relationship x is equal to r times lambda. That is of course the case here with the Plat-Carré projection. And then second, we have y equal to some function of phi, some function f of phi. And this function f of phi could be just r times phi as in the Plat-Carré projection, but it could also be some more complicated function, for example representing this non-uniform spacing of these horizontal lines. And what we can see here is, however, that, well, first of all, every point on the same meridian, so with the same lambda value, will receive the same x value, and therefore indeed meridians will be mapped to vertical lines. That we can see from the first line of this equation, or from this first equation. Then what we can see here is now the y coordinate depends only on the latitude phi. So every point with the same latitude will receive the same y value, meaning just lines of equal latitude are mapped to horizontal lines. That is exactly this property here. Well, and the third property, the equator is scaled with a constant factor, often with 1. That results from this first equation as well. So, well, because, well, yes, if we have, well, of course, if we have for the equator, lambda ranges between minus pi to pi, and then we have in total the length here 2 pi times radius, and that is exactly the perimeter of the Earth. So the equator is scaled then with factor 1. So these three properties, that's the conclusion, can also be inferred from these two equations here. So what is important? These cylindrical projections, they exist not only in this normal position, but also as these transverse cylindrical projections. So there we kind of wrap this cylinder not from top to bottom over the Earth, but somehow we put it to the Earth such that this cylinder touches the Earth's surface in one of these meridians. Then it's called the transverse cylindrical projection. And we can also have arbitrary positions where this cylinder is arbitrarily wrapped around this Earth's sphere, but those are rather uncommon. So most common are these normal positions and these transverse cylindrical projections. So that was already some mathematics. Well, again, a very simple equation. And next I would like to come to the Mercator projection. As I said, it's probably the most important cylindrical projection, if not the most important projection of all. Mercator was this guy here, well, a salesperson actually, living in Germany and Belgium, so what is today Germany and Belgium, and well, he had different names. Krämer he used in Germany. That is actually the German word for salesperson, and the Latin name for salesperson, that is Mercator. So it was, at that time, it was kind of fancy to have a Latin name, and therefore this guy, Gerhard Krämer, used frequently this Latin name Mercator. That's why the projection is called the Mercator projection. It is very important what we will see later. If you see this world map here, first of all, you see that the Mercator projection has, of course, severe disadvantages. Greenland, for example, is extremely large in this projection, the same with the Antarctica. So we have huge area distortions, especially close to the South and North Pole, but still this has its importance, this map projection, and I will come to that later. First of all, we would like to have again this visualization, this geometric construction of this Mercator projection. And we consider again this one column of these surface elements on the Earth, on the spherical Earth. And now, well, what we did before with the Poincaré projection is that we mapped one surface element into one square. That's not done here because, as we've seen before, that causes these changes in aspect ratio and angle distortions. And that's precisely what we would like to avoid. We would like to avoid these changes of the aspect ratios. So instead of converting each of these surface elements into a square, we convert each surface element into a rectangle of the same aspect ratio. Well, here you see this has always a side A and a side B. So here we have A roughly equal to B, so this almost has the shape of a square, and accordingly here we have also a square. But here we have a rather skinny surface element. B is greater than A, and accordingly we have also B prime greater to A prime. So what we do here is that we preserve this aspect ratio. A by B is equal to A prime by B prime. And that way you could construct this Mercator projection kind of manually. Yeah? Take a globe, look at this grid system, a ruler, you can measure this A and B on the globe, and then you draw these rectangles preserving the aspect ratios of these surface elements. With that manual construction, you would not precisely obtain the Mercator projection. So actually, what we did here is looking at these surface elements of 10 degree times 10 degree. If you want to construct the Mercator projection precisely or accurately, then you would need to do this for a finer grid, not 1 by 1 degree, but even smaller, and actually choosing this spacing infinitely small. Then you would have the correct construction of the Mercator projection. Well, that is of course impossible to do this manually with infinitely small surface elements, but that can be done analytically, mathematically. And that is precisely what we will do in a minute. So the more mathematical approach will follow soon. So if we do this construction for infinitely small delta, lambda and delta phi, then we will get the correct Mercator projection. So before we come to the mathematics, let's look at the advantages and disadvantages of this projection. First of all, well, by construction, this preserves the aspect ratios. Yeah, so we have some surface element here. It's converted or transformed into a rectangle of the same aspect ratio. And therefore, if you look at Germany in the Mercator projection, well, as a German I can tell this is exactly my country. Yeah, I can recognize this is what I'm familiar to. And we don't have this strange squeezing in one direction. And this not only implies preservation of aspect ratios, but also preservation of angles. If you look at this angle again here in this surface element, which was displayed in the other visualization, there it would be the same angle still. So that is also called conformal. If you have a map projection preserving the angles or preserving the aspect ratios, that's actually two sides of the same medal. If you preserve aspect ratios, you also preserve angles. Then this map projection is called conformal. One important thing is that angles and aspect ratios are preserved only for small shapes and, well, for small triangles, for example, on the surface, you would preserve the angles with that projection. If you choose a very large region like Africa or something like that, of course you would lose that property, but still the area looks correct with the correct aspect ratio. It appears at least as not being distorted with respect to the aspect ratio. The disadvantages are, of course, the areas are highly distorted. That's already what we've seen earlier on this one slide. And what we can also see is that these lengths of the meridians, they are not preserved. Of course, we don't have these extremely long meridians here. They get extremely long, whereas they should be well, this is actually once around the whole Earth. If you look at the equator, this is once around the whole Earth. If you go from pole to pole, however, that's only halfway around. So there you can see that the distances are highly distorted. Okay, that I would say was all still pretty simple. We were talking about how to construct these map projections manually. That allowed us already to look at the properties of these map projections, like more from a qualitative point of view. What we would like to do now, of course, is doing this more precise in terms of mathematics. Yeah? And there we need to look at this figure first of all. What do we see here? Well, we see the Earth-centered three-dimensional coordinate system x, y, z, which I showed also in the very beginning today. Then you can see here the cylinder wrapped around this Earth, and on top of this cylinder you can see this projected coordinate system, x or small x, small y. That's, if you now unwrap the cylinder and flatten it into the plane, then of course you would have a plane Euclidean coordinate system. This small x, small y, that is our projected coordinate system, which you can see here on top of the cylinder. You can see also here lambda, it's our longitude, it's an angle measured from this x-axis here in this plane of the equator, and phi is this angle here, the latitude, and together phi and lambda define this point here on top of the Earth's surface on our sphere. Then we said, well, with every cylindric projection, or with every cylinder projection, we would have somewhere here on this vertical line, we would have our projected point, our point corresponding to this one. So this point here, it has to be somewhere on this vertical line. That is clear already because we choose a cylindric projection. No matter whether we choose the Plat-Carré projection or some other cylindrical projection like the Mercator projection, this projected point will always be here on this vertical line, well, on this cylinder actually. So the question is just, where is this point? It is a function of phi. we set y equal to f of phi. That was what we said that is true for every cylindrical projection. But what is this f? And that is what I would like to find now with you. Like how to derive this function f from our desired property of the map projection, namely preservation of aspect ratios. We would like to preserve aspect ratios, and with that constraint our aim is to find the function f, defining the relationship between phi and y. And for that, what we do, first of all, is that we look at these partial derivatives. So actually what we can think of, well, this point here, it is defined in 3 dimensions with a vector big X consisting of components big X, big Y, big Z. So that is like this point here. It's this, or actually this vector pointing to that point. That is meant with this vector X. And what we look now is, how does this position change if we change the latitude by some small unit? Well, that is precisely this partial derivative, dx by d phi. That tells us how does the position of this point change if we change phi by some small unit. And similarly we can also ask, like, how does this position of this point change if we change the latitude lambda by some small unit. And by doing that we will get these tangent vectors. So these 2 vectors here, they are orthogonal to each other and they are tangent to the spherical surface of the Earth. And that is an interesting property because these 2 tangent vectors, they span this surface element which we earlier used in our manual construction of this Mercator projection. So similarly what we can do here now, like this point is defined in the map plane with these 2-dimensional coordinates small x, small y. And what we can do again, we can wrap these 2 coordinates into one vector, which is denoted here with this small x vector. And what we can ask again is, like, how does this vector change if we change the latitude of that point by some small value, by some small amount. And again we get this tangent vector which points here in north direction. Yeah, if we increase lambda a little bit, then our point moves further north, so we have this tangent vector tangent to the cylinder here pointing towards the north direction. And here if we have if we look at this partial derivative here, dx by d lambda, then what we ask actually when we compute this is, how does the position change if we change the longitude of that point by some small amount? And we get, well, the surface element not on the sphere, but actually in the map plane, spanned by these 2 vectors, these 2 brown vectors in my figure. And now what we can do here is that we compute now with these vectors. With these vectors we can specify a constraint, or we can specify a requirement, namely what we claim is that these 2 rectangles, the one spanned with the green vector and the one spanned with the brown vectors, they should have the same aspect ratio. And that we do with this equation here. So you can see here that is the vector in these absolute values here, so that is actually then the length of the vector, and again here that is the length of the other brown vector, And by dividing the length of the one vector with the length of the other vector, we get the aspect ratio of this brown surface element. And similarly here, we look at the green surface element spanned by these two vectors. We look at the length of these two vectors, we divide them, and what we have then is the aspect ratio of that surface element. And with the equation symbol here, we say they have to be the same. That is our requirement. So what I'm going to present next is starting with that requirement and now taking an analytical approach. What would be then the correct map projection? What would be the correct function f defining our Mercator projection? Well, what I can do here first of all, to simplify this equation, I'm squaring it on both sides. So then I'm getting rid of these absolute values. They are always nasty. Well, that's a square root actually. Yeah. So with that I get rid of these absolute values and I have just this, what is written here. So that is nice. And well, what I can do next is to compute these terms that you can see here. Well, and that I'm doing again on my whiteboard. Yeah, so what I have here is basically well, let's see. So, how to start? What I would like to compute is actually this sorry. What I would like to compute is this dx by, let's say, d lambda. That is what I would like to compute. That's one term that I need. And well, what was our x? Well, that is, of course, we said this wraps our two coordinates small x, small y. Those were our projected coordinates in the map plane. And that is what we said is the same for every Mercator, for every cylindrical projection. We have something like this. This is f of phi. And here we have lambda times r. So that is what we know. That is the same for every cylindrical projection. And because we say we want from the family of cylindrical projections, we would like one that is aspect ratio preserving. That is kind of our requirement. So therefore we take that equation, and with that we can now compute this partial derivative here. So what is that? dx divided by d lambda. That is pretty simple. So we derive this row by row. The first one derived by lambda is simply r. And in the second one there is no lambda, so that is simply 0. Yeah? And now we can also say what is d small x by d phi. So again, what we do here, the first row derived by phi is simply 0 because we don't have any phi there. And the second row derived by phi is simply f prime of phi. We don't know f yet, but of course formally this is correct. The derivation of f is f prime. So those are already two terms that we needed in our equation, and now we have, similarly, we have this d big X by d lambda. That is what we need. Hope you can see this still. No, sorry. Well, let's see. D big X by d lambda. And for that, of course, it is good to know what was actually our big X. That was in 3 dimensions. So there we need, from our slide earlier, I'm showing that. So that was this equation here, right? That is what we need. So this is r cosine phi cosine lambda then r cosine phi sine lambda and sine phi, or r times sine phi. So that is actually our x vector measured with phi and lambda coordinates. And we need the derivative of this big X vector by lambda now. So what we can do there is, first of all, let's take the first row. There we have minus r cosine phi sine lambda, because the derivation of cosine is minus sine. And here we would have, well, r cosine phi cosine lambda. Yeah, because the derivation of sine is cosine. And finally, the third row, there we don't have any lambda, so that is simply 0. So that is nice. And similarly, we can compute this derivation by phi. Let's do that. So here we have dx divided by d phi. So what is that? Here we have, well, it's actually the same. Yeah? No, it's not the same. It's minus r sine phi cosine lambda. Then we have the derivation of r that is again minus r sine phi sine lambda, and finally this is r cosine phi. So that should be correct. So that is simply deriving these functions. And now I'm erasing this to have a little bit more space. What we need is, of course, also here the squares of this. I mean here, this is actually pretty simple. Here we have dx by d lambda squared, and that is exactly r squared. And the other one here, dx d phi squared, that is simply f prime of phi squared. So what we need here is, of course, also the other terms, like this one here, dx, this should be big X now, by d lambda squared, and that is a little bit more interesting now, because, well, there we have multiple terms. We have this r squared cosine squared phi sine squared lambda plus r squared cosine squared phi cosine squared lambda, and that is equal to, so here we can take this r squared cosine squared phi out, r squared cosine squared phi times sine squared lambda plus cosine squared lambda, and this one here is exactly 1, so that we can forget altogether. Well, and that is interesting, of course. So let's keep that. Like that. And finally, what we need to compute as well, we need this dx by d phi squared, and that is equal to r squared sine squared phi cosine squared lambda plus r squared sine squared phi sine squared lambda. Well, that is again the same as r squared sine squared phi. That is what we can see here. And now we need to add the third term here, plus r squared cosine squared phi, and that is now exactly equal to r squared. So here we have our 4 terms that we need. I'm displaying this now maybe with some other color. We have here this r squared, we have this f prime squared, we have this r squared cosine squared phi, and we have this, we have this r squared here. So these 4 terms, that is our result, which I will now use on my slide. Okay, well, I have to go back to the slide that I used there. That's where we've been. So that is the result I just computed on the whiteboard. I struggled a little bit with the technology, I have to say, switching between these different things, the whiteboard and my laptop, and always watching in the camera. You will see I'm hopefully improving during the semester. But here you can see these are our results, and that we can insert now into that equation here. So that's exactly what we get. Now we can simplify this. We have, for example, r squared here on both sides, and that simplifies then if we take the square root of everything like this. And finally, well, what do we need to do actually to come up with f? Question to you, maybe you know what this will be. Well, we need to compute the integral of that. We have here f prime equal to r divided by cosine phi, and from f prime we would like to compute f, meaning we need to compute an integral. And that's an integral that is not very easy to compute. I would suggest just check your formula collection. Every math textbook has maybe an appendix with some important integrals, and that you will find there as well. So the integral of r divided by cosine phi is this r times natural logarithm of tangents of pi over 4 plus phi half. Well, that's kind of a miracle happening here now, but actually this is just computing the integral of that function, r divided by cosine phi. It took quite long to get there. I hope that you could follow all these very detailed computation steps. And now that we have achieved this here, I would say we have done something really important. What did we do? We defined a requirement, namely we want to preserve the aspect ratios. Then we said we want a map projection from the family of cylindrical projections. So that's how we came up with, well, that's actually how we had this dx by d phi. There we inserted the knowledge that we have a cylindrical map projection. And with that knowledge alone, we were able to find f, namely our mapping function, which defines the relationship between phi and y, our y coordinate. So here you can see that we have, well, the x coordinate here, that is as usual or as always with cylindrical projections, it's just r times lambda. And for the y coordinate we have this complicated equation which we just derived quite step by step and slowly, but I hope with these very small steps you were able to see how we can get to that equation. Well, so what is more to tell about this Mercator projection? Well, often the transverse version is used, of course. We don't use this normal position of the cylinder often, but we choose some meridian arbitrarily here. And then one thing what we can do is that we divide or subdivide the Earth into zones. For example, with the Gauss-Krüger projection that was in use in Germany for quite a long time. There the Earth is subdivided into zones of width 3 degrees, and then for different zones, different projections are used. Well, we have this central meridian, which defines the center of a zone, and for each central meridian, one other position of the cylinder is assumed, and this transverse position of the Mercator projection is then applied. This was in use in Germany until 1991. Still some official points and sometimes these coordinates are still in use, but actually they were replaced by UTM, which is the Universal Transverse Mercator Projection. So UTM is very similar to Gauss-Krüger, except that these zones are not 6 degrees wide. They are not 3 degrees wide, but 6 degrees. And you need to assume that you need to think of this cylinder not wrapping the Earth entirely, but actually intersecting the Earth. And that is by assuming that there's some scaling factor smaller than 1. So with that, the cylinder is a little bit smaller. So that is compensating this enlargement happening when you go further away from the central meridian. So to conclude, we had the Mercator projection now with its mapping function. And we can see this is probably not appropriate for world maps because we have these high area distortions. However, it is really important for smaller zones because it's aspect ratio preserving and especially close to the equator. And in this transverse version of the Mercator projection, there it's most important because then you choose the central meridian close to your area of interest, and then you apply the corresponding transverse Mercator projection there, where you have then only small distortion close to that central meridian. Okay, similarly, we can actually compute other map projections, not just the Mercator projection, but let's think of a map projection with some other nice property. For example, we would like to have a cylinder or cylindrical projection that is preserving areas. Yeah, not aspect ratios and angles, but areas. And again, we can construct such a map projection manually. We look at this grid of lines of equal latitude and meridians. And what we do now here, that each of these surface elements is mapped into a rectangle of the same area. So here we have somehow A and B, and here we have A prime and B prime. And our requirement is that the area of these elements here is the same. So, of course, the area of a rectangle is just the product of width and length. So A times B should be equal to A prime times B prime. That is now our requirement for the area preserving cylindrical projection. But we can use the very same approach as before. We look at the same figure here, we look at the same partial derivatives. We have another or a different requirement now. We say not the aspect ratio of these two sides of our surface element should be the same, but we say the sizes of the surface elements should be the same. So we take the length of one vector times the length of the other vector, and that is what gives us the size of the surface element. And that should be equal to the size of the corresponding surface element on the Earth's surface, on the sphere. So that is our requirement here. Well, so what can we do there? Again, well, you see, it's going to be much simpler here if we square both sides. Then we get rid again of these absolute values. And now we have exactly the same 4 terms as before, which I computed here on the whiteboard, right? And we can insert these terms there, and we will directly get to that equation here. And now it's quite simple actually to solve this equation. We can see already that this r square here can be removed because we have r to the 4 here on the right hand side, and we can take the square root after that, of both sides, so then we have f prime of phi equal to r times cosine phi. That is now our, well, interim result, I would say. We are not yet done. Again, what is here is the derivation of f, but we are of course interested not in the derivation of f, we are interested in f. So we need to compute the integral again of r times cosine phi. And that is probably something that you can do yourself without looking in a collection of formula, for example, or in a math textbook. You should know that the integral of cosine is actually sine. So, and then the integral of r cosine is r sine. So, and that is our result. Actually, if you take an integral, you could also always add also one constant c. Yeah? So that would also be correct if we say f of phi equal to r times sine phi plus c would still be correct. But what we would like is, of course, that the equator is mapped to y coordinate 0. And with that additional requirement, this constant c becomes 0. And we have then the equation f of phi is equal to r times sine phi. Well, that was much quicker now. I think that it was kind of worth it to spend so much time on computing these 4 different terms, because you need them quite often with different map projections. Here again, it's not the Mercator projection, but the area preserving cylindrical projection, or the cylindrical equal area projection. And using the same approach, we got to the result, to the map projection. Yeah, we have this requirement, and we say our mapping function should be from the family of cylindrical projections, and with that information, that was sufficient to get to the result f of phi is equal to r times sine phi. So again, here you can see the result. Well, this x equal to r times lambda, that is true, of course, for every cylindrical projection. But this second equation here, that is what we have found ourselves with our approach, given this information that we want an area preserving projection. That's how we got there. So y is equal to r times sine phi. And if we apply that to the whole Earth, you will get a picture like that. You can see actually that the distances between these lines of equal latitude, they get smaller and smaller towards the poles. Right, before I come to the next slide, I would also again like to switch to the whiteboard. Well, this is kind of messy now, but I can clear it like that. Just to give you an impression how this equal area map projection actually works. Okay, so here we have our Earth, should be a sphere. Here we have the center of the Earth. Here we have maybe our point P. And here we have our cylinder. Like that. And here we have phi. So the question is, where on this cylinder shall I place this P? This point P. Or let's say, well, this is P, and where's the P prime, meaning the projected point? Well, what we had there is this y is equal to r times sine phi. That is the equation of the equal area projection, the cylindrical equal area projection. And interestingly, we find the r, of course, here. And then we find this r times sine phi here. So that means to get to this equal area projection, all what we need to do is project horizontally. So any point here on this Earth, we just need to project horizontally to this cylinder, and that's how we get our projected points. So here the term projection can be thought of actually as projecting something from the Earth's surface, like in a constructive approach to the cylinder, because we project horizontally. In the Mercator projection, that is not possible. There's no simple projection how we could get, for example, from this point P to the corresponding point P prime. There is this functional relationship, of course, between this phi and the y, but as you have seen with this Mercator projection, that is a rather complicated function, a rather complicated mathematical relationship where there is no such easy geometric interpretation of it. So that was everything I wanted to tell about the cylindrical equal area projection. Of course, it is a nice projection for the Earth, for thematic maps, for example, where you would like to show, for example, let's say population density, then you can map it on countries represented as polygons in that projection, without giving the impression that maybe there are so many people living in Greenland, which of course would be incorrect. So, and with that I'm almost done with my presentation. So of course there would be much more to tell about map projections. I have focused here just on cylindrical projections, 3 in detail, namely the Plat-Carré projection, the Mercator projection, and the cylindrical equal area projection. It was important for me to show you this mathematical approach, how to get to the equation that defines the map projection. There are many other map projections, of course, especially for world maps. In cartography, sometimes you want to depict the entire Earth, and then none of these cylindrical projections is really working well. So there's, for example, this Robinson projection. You can see immediately that this is not a cylindrical projection because the meridians are not displayed as vertical lines. We have these curves here instead, right? And therefore, well, with the Robinson projection, well, that would be a new chapter, so to say, in this lecture. However, since there was just this one lecture about map projections, I took the focus to this more mathematical approach for these more important cylindrical projections. This Robinson projection, it tries to find a good compromise between area preservation and angle preservation, or area distortion and angle distortion, right? But there's no map projection that would preserve both. So somehow we need to accept some kind of distortion after all. To conclude, we can also conclude or finalize this big picture showing the relationship between these different types of coordinate systems. Here you can see not the relationship with the Plat-Carré projection, but the Mercator projection, which we derived in this lecture. And this is applied very often in geographic information systems. So geographic information systems are really good in combining data sets from different sources, maybe even data sets with different spatial reference systems. And think of this application here. Well, we may have a data set This could be a German cadastral data set with building footprints and real estate boundaries. This would come probably in UTM coordinates corresponding to the ellipsoid GRS 80 and the Earth-centered system ETRS 89, the Earth, the European Terrestrial Reference System from 1989. And on the other hand, you have probably a data set of forests, maybe coming from, let's say, OpenStreetMap. As there we have global projection Mercator, it's ellipsoid WGS84, which is in common use, well, with the OpenStreetMap community. They work, of course, much with GPS, for example. Their WGS84 is important, and that also has a corresponding Earth-centered system, WGS84. So now somehow we would like to combine these two data sets in one map, and that is one important, or one of the most important functionalities of geographic information systems, to combine different types of information. So to do this, we need to go through a rather long pipeline of transformation, and that you can see here. So first of all, what we need to do is, of course, we need to convert maybe these Mercator coordinates here into phi and lambda, into ellipsoidal coordinates related to WGS84. So now we have these ellipsoidal coordinates. Those we need to compute or transform into these Earth-centered three-dimensional coordinates. Then we have a different three-dimensional coordinate system here. So there we need to compute 3 rotations and translations, probably even a scaling. So that needs to be done to convert the coordinates from this system into this one. Then again, from here we need to compute ellipsoidal coordinates, latitude, longitude. And then we can project using the UTM projection into the map plane. And finally, we are there that we have our forest now also in this cadastral data set. And that is, of course, most important to know as a geodesist. That was my presentation for today. Unfortunately, there is no option for you to ask questions now. Of course, you can use probably the chat or email me. But hopefully we will see each other live here in Bonn in person, so we can also discuss about this topic, especially also about geographic information systems in the corresponding lecture of the first semester, Geodetic Engineering. Thank you very much, and bye-bye.